we can consider the continuity equation so that we can define mass flow rate in terms of velocity and area, and that'll be handy for us. We remember that the continuity equation is mass flow rate equals A times V, Q equals AV. Q equals AV in, Q equals AV out. Q remains constant, the same everywhere, the flow rate. We can't change the flow rate because we're not squeezing anything, we're not compressing anything. So if the area increases, the velocity decreases, and vice versa. Looking at this for a steady flow situation where there's mass flowing in and out, we can say, okay, the mass is sitting in this tube. The tube has a cross-sectional area at the front and the back. So the contained mass inside there is just going to be its density times its volume. The contained mass inside any tube is going to be its or any shape at all. It's just going to be its density times its volume. That's how much mass is in here. It's density times volume. But volume is cross-sectional area times length. That's how you calculate the volume. So now density times volume, well, density times area times length, delta X. But now we're going to remember that, what did I do here? Let me see. Distance is velocity times time. So instead of just distance delta X, I said velocity times time. Distance is velocity times time. That comes from velocity equals distance over time. So substituting that in for delta X, I have velocity delta T. Now, absolutely, this is a derivation, and I knew what I was doing, and I knew what I wanted to get to. So now, instead of representing mass flow as the sum, in an energy form as the summation of the amount of mass times its enthalpy plus the mass times kinetic energy or plus mass times potential energy, I can represent mass as density times area times velocity over time. And that's really handy to me in a first law energy balance. Because now my first law energy balance, if I were to do it per unit time, in my first law energy balance, for each unit of time, I can just use the density. Here's what the material is. Here's how much of a cross-sectional area it's going through. And here's the velocity it's traveling. That'll tell me how much mass is flowing over that time. I can then apply it to different shapes, and I can figure out how much mass is flowing in this from this big cross-sectional area to this small cross-sectional area, because this term is different on the inlet and the outlet. So now this is the equation that, or these are the terms I can be putting into the first law energy balance when I have a steady flow system with mass flowing into and out of a system.